Hello, my name is Matthias Barkowsky, and I'd like to welcome you to my presentation of the joint work that I did together with my colleagues Thomas Brandt and Professor Holger Giese, and which is titled Improving Adaptive Monitoring with Incremental Runtime Model Queries. I assume that in this audience everyone is familiar with the MAPK loop for system self-adaptation. So to provide a bit of context, we're focused on the part of the loop that is concerned with the detection of symptoms that indicate issues for self-adaptation. That is the monitor and analyze phase and the knowledge base. Specifically, we assume an architecture runtime model as part of the knowledge base, which is extracted from a monitored system using data provided by system sensors, and which can, by different query mechanisms, be queried for the symptoms that we're interested in. In previous work, we have introduced an improvement to the monitoring phase, which we call adaptive monitoring, and which allows the query mechanism and the query execution to influence the activation and deactivation of sensors, thereby saving sensing effort. To provide a brief example, on the left you can see a representation of an online auctioning system that consists of tenants that have services which can be instantiated. And in the top right, you see a query specification for a potential symptom that could indicate an issue for adaptation, where we look for a tenant with a sufficiently high revenue that is connected to a service with an instance that exhibits anomalies. Now, if the sole purpose of a runtime model extracted from this monitored system is to answer this query, then we can see that some of the system's components don't actually have to be represented there. For instance, we can leave out this filter component as it doesn't even appear in the query specification. And even going one step further, just by looking at the revenue value of the tenant, we could already conclude that there is no result for this query specification, and therefore we could even omit the service and the instance components. Doing that, we could then obviously also deactivate the sensors that are concerned with extracting the corresponding data, which is indicated by these gray circles. And effectively, we only have to turn on one sensor that tries to collect this revenue property of the tenant T1, which is indicated by a green circle. Now, in our technique for adaptive monitoring, the idea is to only turn on those sensors that correspond to properties that are actually accessed by the querying mechanism as it executes the query specification. Therefore, the effectiveness of that technique obviously also depends on what kind of query mechanism is employed. Previously, we have mostly considered local search as the query mechanism, but recently we've turned our attention to so-called retinets, which are a very popular and widely used query mechanism in the context of model-driven engineering. A retinet is effectively a decomposition of a query into simple subqueries, which are organized in this kind of network structure that you can see on the right, where the so-called input nodes at the bottom represent primitive subqueries that only consist of a single connector, such as the connector between the tenant and the service, and which then extract matching connectors from the queried runtime model. These intermediate results are stored in so-called indices and can be further processed by other nodes in the retinet, such as selection nodes like this sigma1 node, which are responsible for checking the constraints defined in the query. And finally, there are so-called join nodes, which compose pairs of compatible intermediate results into more complex ones. When working with these retinets, we noticed that in conjunction with our adaptive monitoring approach, the adaptive monitoring often effectively degenerates to monitoring everything, as you can see here in the top right corner, where all the system sensors are active. The reason for that is that the input nodes of the retinet basically blindly extract and also globally extract all matching elements from the runtime model, thus accessing large portions of it, and thereby activating monitoring. So in this work, we have tried to tackle the research problem of how to enhance the reti query mechanism to better exploit our adaptive monitoring approach. Therefore, we have chosen to enhance or adapt existing retinets, as we'll see now. Our adaptation or enhancement is based on the observation that one dependency of a join node in a retinet can effectively act as a filter for the intermediate results that have to be computed in the other side of the join. The reason being that the join only composes pairs of compatible intermediate results. So for instance, if we don't have a compatible intermediate result for some tuple in the right part of the join, in the left part, then that tuple in the right part effectively doesn't contribute to computing any overall result and is somehow superfluous. So in the first step of our retinet enhancement, we analyze an existing retinet and for each of its joins designate one of its sides as the filter side. Subsequently, we then insert what we call so-called projection filter structures, which consist of a projection node and a local navigation node, which effectively apply that filter from one side of the join to the other side. To see how that works, we can look at the execution of the enhanced retinet, which, like the standard retinet, starts with the execution of the now that's or the only input node of the enhanced retinet, which extracts this connection from the tenant to the service, which is stored in the index. And then that tuple is further processed by the selection node sigma1, where the constraint over the tenant revenue is checked. And as the check fails, the tuple is not propagated further and the execution is finished. So now in contrast to the standard retinet, we have skipped the execution of this entire right part of the retinet, and thereby we were also able to keep the monitoring for these two properties, the outgoing edge or the connector of the service and the number of anomalies of the instance, inactive. However, this does not compromise the completeness of the overall query results, as we can see when the revenue of the tenant switches to high. This causes the propagation of this tuple T1S1 through the selection node and then the projection filter, at the end of which our new local navigation node extracts the connection between the service and the instance. In the end, the net therefore produces or correctly produces the overall result. Interestingly, the enhanced retinet also affords pretty fine-grained control over the deactivation of monitoring, which we can see when the revenue of the tenant switches back to low. By tracking the propagation of the change through the network, we can tell pretty precisely which properties and when they become obsolete, and the corresponding monitoring can hence be deactivated, like this connection property of the service, for instance. We have prototypically implemented an automatic adaptation of existing retinets as described and evaluated it in the context of a simulator for architecture runtime models that are similar to example, using a query that is also similar to the example query used in this presentation. And our initial evaluation results indicate that the enhanced retinets, which are displayed as a solid black line, significantly outperform the baseline retinets, which are displayed as a gray dotted line for both sensing effort and querying effort. So in conclusion, our contribution is an enhancement of retinets with the aim of better exploiting our adaptive monitoring approach, thereby minimizing sensing effort and, for our example, also reducing querying effort. However, this reduction in querying effort is not really generalizable. In fact, the aggressive deactivation of properties and connected potentially expensive deletions from the enhanced net's indexes may even increase the querying effort of the enhanced retinet. Furthermore, we can't, as in previous work, treat the querying mechanism as a black box anymore, because in order to employ the enhanced retinets, we have to modify a reti-based query mechanism. In future work, we plan to extend our currently very simple evaluation, also considering monitoring activation times, and furthermore lift some of the restrictions that we currently impose on the retinet structure that acts as the baseline for the as the base for the enhancement. You can read more on that in the paper, obviously. All right, so thank you for your attention, and I'm looking forward to the discussion in the session.